Hi, welcome back to AP Chemistry. You're here with Mrs. Mays, and we're working on acid-base equilibrium. Today we're going to look at the topic of buffers. Buffers are solutions in which the pH remains relatively constant even when small amounts of acids or bases are added. There's two kinds of buffers that we could have. We could have an acidic buffer, which is composed of a weak acid and one of its salts. Or, of course, we could have a basic buffer consisting of a weak base and one of its salts. The buffer capacity simply describes the amount of acid or base that could be added to a buffer before a significant change in the pH occurs. Buffers have the ability to acquire or to give away a hydrogen ion, and that's how it allows the solution to maintain a standard pH. Here's an example of a buffer system that's pretty common, the acetic acid and acetate buffer system. When the acetate ion is placed in water, it will acquire the hydrogen ion from the water and produce acetic acid. Then the acetic acid can react with a hydroxide ion in the water, and that creates water and the acetate ion, and that is supposed to be CH3COO. Both reactions occur simultaneously in order to maintain pH. We have both the acetate forming the acetic acid and the acetic acid forming the acetate, and that's how whether we add an acid with hydrogen ions or a base with hydroxide ions, the system of acetic acid and acetate can absorb either one. To determine the pH of buffers, we simply use the common ion effect like we would in a normal rice table for equilibrium. But another option we have is to use what's called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation equates the pH to the pKa of the acid plus the log of the conjugate base and your weak acid in your solution. So the weak acid and its conjugate base, you just put their concentrations in, and you can use the Henderson-Hasselbalch equation to solve the pH. I'm going to use the common ion effect rather than the Henderson-Hasselbalch, but then when we talk about how to create a buffer, you'll see me use the equation. So suppose that we want to create that acetic acid and acetate buffer like we said before. So the weak acid is acetic acid. It can react with any hydroxide that's in the solution. The sodium acetate forms the acetate ion in solution, and that can take on any extra hydrogens that would lower the pH. So let's calculate the pH of a solution that is 0.5 molar acetic acid and 0.25 molar sodium acetate. We know the Ka, so let's make the rice table. Let's form hydrogen ions in solution. So I'll start with acetic acid, and we'll put it in some water. And that will raise the hydrogen ion concentration by forming hydronium ions and acetate ions. So there's our reaction. Our initial conditions are given to us in the composition of our buffer. So it is 0.5 molar acetic acid. The water doesn't get to count. Hydrogen ions or hydronium ions are not there yet, but the sodium acetate already has 0.25 molar. So we know we'll lose some of our acid and gain some hydronium ions and gain some acetate ions. So we put this into our equilibrium expression and we solve. The Ka is going to be products over reactants Don't forget to put charges on all your ions or you don't get it right. And that's equal to our Ka of 1.8 times 10 to the negative 5. So we could use the small x assumption in solving this problem. So we would have x times 0.25 plus x, which is essentially just 0.25, all over 0.50 minus x, and again, with the small x assumption, we could just call that 0.5. And that allows us to rearrange to solve for x. Okay, so 1.8 times 10 to the negative 5 times 0.50 over 0.25 will give us x. Great, so x is equal to 3.6 times 10 to the negative 5. And x is here representing the equilibrium concentration of the hydrogen ions. So we are almost to the answer to our question. We need the negative log of hydrogen ion concentration so that we can determine the pH. So we take the negative log of 3.6 times 10 to the negative 5, and we get that the pH is equal to 4.4 in this buffered solution. So using the common ion effect allows us to solve problems with buffers. Let's try another one. Here's a basic buffer because now we're using the weak base ammonia and the conjugate acid ammonium in the form of ammonium chloride salt. So when we add the weak base, then we can react with any extra hydrogen ions there might be in the solution so that we can absorb any lowering of the pH by reacting it with the weak base. On the other hand, if hydroxides are added to the solution, the ammonium ion will be able to react with those to form water and use them up. So we'll calculate the pH of our system that has ammonia and ammonium in it, the weak base and its conjugate acid. So first we start with our reaction. So NH3 in water reacts, and we get ammonium, those ions, and we get hydroxide ions. So initially our buffer contains 0.25 molar ammonia and 0.40 molar ammonium, and no hydroxide yet. Then we have a change where some of the ammonia is reacted, so I gain ammonium and I gain hydroxides. And then what do we get? 0.25 minus x, 0.4 plus x, that is, and then x for the hydroxide. So we have a little extra step, but it's no big deal. We know that Kb, since we have hydroxide, is equal to 1.8 times 10 to the minus 5, and that is going to be our products over reactants. So 0.40 plus x times x all over 0.25 minus x. Our equilibrium value is small enough that we can use the small x assumption. So to solve for the value of x, I'm going to rearrange. X is equal to 1.8 times 10 to the negative 5 times 0.25 over 0.40. And that gives us, all right, so we're going to put in 1.8 times 10 to the negative 5 multiplied by our ratio 0.25 over 0.4, and I put that in parentheses just to keep that all together, and I get 1.125 times 10 to the negative 5. 1.125 times 10 to the minus 5 molar. And that X is equal to the concentration of hydroxide ions at equilibrium, right? From our rice table. So now I can get the pOH if I take the negative log of that concentration. So we come back to the calculator and do the negative log of our answer from before. And we get 4.988, blah, blah, blah. So the pOH is 4.95, and we'll turn the pOH into a pH. So pH is 14 minus the pOH, or 14 minus 4.95, which gives us a pH of 9.1. So again, the common ion effect allows us to determine the pH of our buffer for any type of mixture. But part B says, what is the effect on the pH when 0.02 moles of sodium hydroxide is added to 300 milliliters of this buffer? So when we have this type of problem, we have to worry about the stoichiometry first, and then the buffer system next. So stoichiometry first, then equilibrium. So when we add sodium hydroxide, we know that that's going to react with the weak acid, right? The NH4Cl is the one that's going to be reacting with the hydroxide. So if I have, let's see, how many moles of NH4Cl? That would be in 300 milliliters, or 0.300 liters. And my molarity from before was 0.4 molar, then that gives us 0.120 moles of ammonium chloride. And now let's see, our reaction says sodium hydroxide is added to our buffer, and we get a double replacement reaction, so NH4OH plus NaCl. And of course we've got spectator ions here, right? And this NH4OH, when it forms in double replacement reactions, actually decomposes and forms ammonia and water. So we don't really have ammonium hydroxide, we just have ammonia and water in our system. So now we set up a new equilibrium with new amounts. So we've got sodium hydroxide in our solution, we've got ammonium, we have ammonia, and we have water. Okay, so we had 0.02 moles of sodium hydroxide reacting with 0.120 moles of ammonium chloride. So which one is the limiting reagent? It's a 1-to-1 mole ratio, so we know that the hydroxide will run out first. So we lose 0.02 moles, and here I lose 0.02 moles, and here I form 0.02 moles, and water, you know, it's forming 0.02 moles, but that's not going to show up in our equilibrium. So I have none left of my hydroxide. I have 0.100 moles in 300 liters, and here I have 0.02 moles plus what I had before. What did we have before? I have to look. 0.25, okay. Oh no, I had 0.25 molar. So 0.25 times, we have 300 liters, so that's 0.75 moles, right? So 0.02 plus 0.075, so 0.02 plus 0.75, not 0.75. And that's moles in 300 milliliters. And then my water is not going to make any difference in our solution. Okay, so we take care of moles first, then we take care of stoichiometry. So I'm going to put these up here so I don't lose them. Hydroxide is 0. Ammonium is 0.10 moles in 300 liters. So that gives me 0.33 molar. And my ammonia, I had 0.02 plus 0.75 in 300 milliliters gives us 0.32 molar, and then water doesn't have a concentration. So now let's look at our buffer system once we have disrupted our buffer by adding sodium hydroxide. So now I've got ammonia in my water, and we still have ammonium ions in our buffer and some hydroxide ions that will be formed by the dissociation of this base. So we get 0.32 molar here and 0.33 molar there. I have it written all crazy like. So that was this number and that was this number. And then I lose some ammonia and I form some ammonium and I form some hydroxide. So at equilibrium it is 0.32 minus X and then 0.33 plus X and X. So far so good. Now at equilibrium we use the Kb because we have hydroxide, so that was 1.8 times 10 to the negative 5. And we will have products over reactants, 0.33 plus X times X over 0.32 minus X. So rearrange to solve for X, and I got a concentration of hydroxide, which is X, equal to 1.75 times 10 to the negative 5. So our pOH is the negative log of that number, which gives us 4.76, and we need to find the pH, and that will give us 9.2, 14 minus 4.76, right? So in our buffered solution, the pH was 9.1. And when we added hydroxide, the pH only went up to 9.2. So we say our buffer system is going to resist dramatic changes in pH. And maybe I haven't convinced you yet. So let's see what happens if we were to add the 0.02 moles of hydroxide to just plain water instead of putting it in our buffered system. So what if we had just sodium hydroxide in water instead of putting it in our buffer? So sodium hydroxide will break apart in water to have sodium ions that don't do anything to the pH and hydroxide ions that will raise the pH, right? So if I have 0.02 moles of sodium hydroxide, that gives us 0.02 moles of each of these ions, sodium and hydroxide ions. So the concentration of hydroxide ions corresponds to 0.02 moles in 300 milliliters, or 0.300 liters of solution, which is 0.067 molar. Now we can determine the pH from the pOH. So the pOH is equal to the negative log of 0.067. And that gives us a pOH of 1.18. And of course the pH is where we take 14 minus the pOH. So 14 minus 1.18 gives us a pH of 12.82. So adding sodium hydroxide to just water results in a change from 7 up to 12.82. That's a much more dramatic change than going from 9.1 all the way up to 9.2. So that's how the buffers allow us to maintain homeostasis in our environment or in our bodies or wherever it is that we need the pH to remain constant. So buffers are really important. Here's an example. There's a buffer in your bloodstream that has to do with the levels of carbon dioxide in your blood. So if carbon dioxide levels increase, then it combines with water to form carbonic acid in your bloodstream. And the carbonic acid dissociates to form the bicarbonate HCO3 ion and hydrogen ions. pH sensors in your capillaries, in your blood vessels, detect the drop in pH due to an increase in the hydrogen ion concentration, and they send a signal to your brain which forces you to breathe. So if you're breathing in nitrogen instead of oxygen, then that doesn't cause a change in the hydrogen ion concentration, and you don't get this desperate signal of, hey, you need to breathe. But when you're holding your breath, your brain can go into panic mode because your pH sensors are going crazy, sending signals to your brain that you need to take a breath. Buffers are important.